Now your favorite. This is what you guys have been waiting for this. Some applications. People always ask, when am I ever going to use this? Ever? And I'd be like, what if you're in a boat that's looking at a cliff and you can measure these angles and you want to know how far away from the cliff you are? What's that? Yeah. Why wouldn't you want to know? Like, right? Just like, what if you're on a boat and you see the smoke coming off the smokestack of the cruise ship? You know? You're gonna be glad you had this class. All right. There's a cliff and a lighthouse that is perched atop said cliff. There's a boat somewhere off at sea, and they've measured some angles. So the way that this is described, it kind of looks like, I'm just going to have a go at sketching this. Here's my best cliff. That's my cliff. All right. It has some unknown height. We don't know the height. That's one of the things they're asking us to find. And we'll assume that that's a nice straight cliff. And here's the water. And here's the boat. That's my boat. Okay. Now there's also a lighthouse that is 50 meters tall. So there's my lighthouse. We know that's 50 meters. And the angles that we know are the angle from the boat to the top of the cliff. That is 15 degrees. And then the angle from the boat to the top of the lighthouse is 9 degrees. Oh no, is that what it says? No, I already did the subtraction. The angle from the boat to the top of the lighthouse is 24 degrees. We can then infer from that that this little sliver of an angle in between is 9 degrees. So we want to know two things. In part B, we want the height of the cliff, so I've already labeled that H. The other thing we want is the distance from the ship to the cliff. So I'll call that X along the bottom. We want to find X. So we have two right triangles here. Neither one of them with enough information to actually use SOHCAHTOA or Pythagoras on, though. The only side measurement we have is a side of an angle that is not a right triangle, right? That 50 meters. So the first thing we're going to do, I'll highlight this in red, is look at this triangle, this little kind of skinny guy here, because that's the only triangle for which we have a side measure. And we can, so we know the side measure and we know the angle 9 degrees. Okay. That side measure of 50 meters is opposite this known angle of 9 degrees. This guy is screaming out law of sines because I have that side angle pair. And we can use it to solve, well, for either of the other two sides, I guess. Let's see. We know, we need some more information. Well, we have more. We have to glean out some more information. We're assuming that this is a nice right angle at the water. And if this is 15 degrees in this corner, we know this angle, right? What should that be? What's 90 minus 15? 75. And if we know that angle, then we know this angle, the obtuse angle of the sliver triangle, because they are supplementary. So 180 minus 75 is 105, and that means we know this angle at the top too. 105 and 9 is 124. What's 180 minus 124? Is it 50? 66. All right, so we know all the angles of the little triangle, which means we have our pick of which of the two sides we're going to solve for. I think either of them, will work just fine. I think we'll go ahead and solve for the lower side. I'll call it Z here. And I think, either would work, right? We could solve for either of the other two sides. I like solving for z here because knowing z gets me a side in this lower right triangle, of which h is a side. If I use the top side, then h is not actually a side length, it'd be h plus 50. That's the vertical side of the bigger right triangle. So let's find z. So let's see, our matched pair, we have 50 over sine of 9 degrees is, now the angle opposite side z is the 66 degrees, so this would be z over sine of 66 degrees. We can multiply both sides by sine of 66 degrees. And that gives us z is 50 times sine of 66 over sine of 9 degrees. $291.99. And it would be in meters. It would inherit the linear units of the height of the lighthouse. So this value for z is neither of the two things we're asked to find, but now I think we have the rest of it will fall out nicely just using SOHCAHTOA. So the rest of it is to just solve. So this is phase 1. Phase 2, let's solve the right triangle. What do you want to find first, h or x?
X.
X. So if I'm solving for x, and I know that I want to find x, I'm going to use my 15-degree known angle, and the other side we know is the hypotenuse here. What function do we want to use? Yeah. So on SOHCAHTOA, cosine says cosine of 15 degrees adjacent over, so that's x over 291.99. And Emily is asking, was it 180 minus 124 for the angle near 50? Yes, it was. So we did 180 minus 105 minus 9 to get that angle, which is 180 minus 124. Wouldn't it be 56? Nope, I get 66. Oh, 105 plus 9 is 114, not 124. It is 66 degrees is the correct angle. I incorrectly added 105 and 9, so that was my bad. All right, good catch. So we multiply both sides by 291.99. And we get that x is cosine of 15 times 291.99. What did anybody do this out? 282. And this would be meters. So this is the answer to part A. And for the answer to part B, we want the height. We just go use SOHCAHTOA again, but this time which function do we want to use? Yeah, sine. So that's the height over the hypotenuse, 291.99. So the height And what do we get for this? What is it? 75.6? And that's the answer to part B. So far, so good? Okay. Now, when you're in a boat, you have the ability to find out all these things. One more problem to get through. This is like a vector problem, but so some vector problems lend themselves nicely to solving by using oblique triangles. So that's what we're going to do in this problem. And in particular, I'm going to write a little note. I think you should write it down too. You will use this to help with problem 9, number 9 on the problem set. So we have 2 ropes supporting a crate. They give us the tension, so that's like the magnitudes of the vectors. And we're being asked to find what is the angle in between the 2 ropes. So conceptually, what we need to realize is that if this crate is just hanging there, it is not moving, right? That means it is in equilibrium. And if the, for example, if the like X components did not balance each other out completely, it would be a motion either left or right. Or if the Y components didn't really balance each other out, it would be, you know, moving upward or downward. So that will help us sketch these vectors in the plane, because we know vectors begin at the origin. And these vectors, the idea with this being in equilibrium is that when these vectors, when added together, completely even out the 35.5 kilogram force downward. So we have one vector. I'll call the 17 kilogram vector, I'll call this T1, and the other vector I'll call that T2. So I've got T1 here. And T2 is added to it. Now here I'm really going to think of vector addition as adding them tip to tail. Yeah, I know that T2 exists somewhere over here, but I'm going to draw it so that it's added tip to tail here. There's my T2. And the conceptually, the fact that this is in equilibrium means that when I draw T2 so that it starts at T1, it exactly has to end on the y-axis, because I know those x components have to cancel each other out. It's in equilibrium. Not only that, but the overall upward component of the resultant vector that we get has to completely balance out the 35.5 kilograms downward. So I know that the overall upward, like y component of the resultant, is 35.5. These vectors added together just have to equal the vector that's 35.5 kilograms straight up. So I know that the T1 magnitude is 17. I know that the T2 magnitude is 23. And we want the angle between the vectors, which is, let's see, which would be, if we're looking at these vectors starting from the origin, what we really want is this angle here. We're going to do that initially by finding this angle here. I'm going to call this vertex A, or angle A, so that this side here is little a, and I'll just call this one B and this one C. In these vectors that we're adding together, basically we have a triangle where we know all 3 sides but no angles. That's totally a law of cosines problem. So if we're going to find angle A, we'll use the law of cosines that starts with a squared equals. What goes on the other side? Times cosine of A. Yep. All right, let's go to town. We're going to find cosine of A, so I think I will do the algebra first. If I throw the 2bc cosine of A on the left and subtract A squared from both sides, we get the following. And then we divide by 2bc. And now let's throw these numbers in. So side B, 17 squared plus 23 squared minus 35.5 squared divided by 2 times 17 times 23. Well, I should probably, yeah, okay. So negative 0.5655. We can find angle A by taking the arc cosine. Oh, whoops, I did not put in the negative. $124.4. Now this isn't quite the angle that we're looking for. It is angle A as we have labeled it. So I'm going to scroll back up. We did find angle A. The angle we want is this one though. So if I just sort of extend like the T1 vector and I'm going to draw the horizontal, right? So this is like parallel to the x-axis. What I really want is this angle. So let me think. Oh yeah, okay, actually let me extend it down the other way. Like I'll extend T1 down this way, below. So if we found angle A here, that's the same as this angle. But of course T1 is a straight line. Like these angles have to be supplementary to each other. So that means that to find our angle, the one that we desire, we just need to subtract the angle we found from 180 degrees. So this is the 104.4, and we want one in red. So we'll just find the supplement. Oops, 124. Why did I write 104? And this gives us 55.6.